All right, and welcome back, everybody. So we just spent a lecture talking about some important properties about eigenvectors and their linear independence, along with a quick recap of diagonalizability. And we also showed how diagonalizability relates to completeness, and it turns out that these two concepts are identical. So completeness and diagonalizability are great concepts, and we need to be able to find these natural eigenvector coordinates that our matrices would prefer to use when we use matrices for multiplication. So what we're going to do in this lecture is show you how much more or how much better we like symmetric matrices than we do just arbitrary dense matrices. And the following exposition is specifically for symmetric matrices, but a similar line of argument is extendable to self-adjoint matrices. So matrices who are equal to their own conjugate transpose. So you'll see this either as a star or a dagger for you physicists out there. Right, this is a Hermitian matrix, or Hermitian, depending on your pronunciation. Charles Hermite was a French mathematician. So an Hermitian matrix is a matrix that is equal to its own conjugate transpose. And these self-adjoint matrices are some of the most powerful objects that we have in linear algebra, most well behaved. And the goal of this lecture is to show you how well behaved these matrices are and why we would like to use them whenever possible. So let me motivate it. I'll show you, so recall that we had our usual setup that this matrix 4 by 1 by 4 is indeed a complete matrix. It has two distinct eigenvalues, therefore it has two complete eigenvalues because this is a two-dimensional matrix. And you can actually go ahead and diagonalize this guy pretty quickly. So no problem here. If I was doing this in MATLAB, all I would have to do is come up with eig of A, and that'll give me the eigenvalues in here. So diag of eig A is going to be this matrix D. In the latest version of MATLAB, I don't know which version that is, so forgive me. But we can go ahead and compute eigenspaces once we have those eigenvalues and fit them into the matrix S, which is on the right here. Okay, so we do have a diagonalizable matrix because it's a complete matrix. So if we use our standard inner product space for R2, notice that these two vectors, V3 and V5, are actually orthogonal to one another. So not only do we have a linearly independent set of eigenvectors, these guys are actually even better behaved. They are orthogonal. So this is an orthogonal basis. And we know from chapter 4 how much we like orthogonal bases. Oh, do we like orthogonal bases? I have a theorem for you that tells you how easy it is to get these orthogonal bases. But it requires that we have symmetric matrices. This is not a complete characterization. This is not an if and only if. So just because you have an orthogonal collection of eigenvectors does not necessarily mean that you are that you come from a symmetric matrix. But if you can guarantee that your matrix is symmetric, then you get a whole bunch of really, really great properties about this guy. First and foremost, the eigenvalues of a symmetric matrix are real. So we don't run into this problem of there being complex conjugates or complex conjugate eigenvalues. So we don't get weird rotational behavior as opposed to scaling and dilating behavior, or extension and dilation behavior. So that even counts for the complex matrices. If we have a Hermitian matrix, right, then this still applies. So even though all of your entries are complex, if you are a self-adjoint, Hermitian, whatever term you want to use, if you are equal to your conjugate transpose, then even though you are complex, your eigenvalues are all real. Physicists make a dramatic use of this, a very powerful use of this fact when they define what are called observables in quantum mechanics. So there is a full linear algebra theory behind quantum mechanics, and is definitely abstract, but very, very powerful because of it. So not only do we get real eigenvalues, but the eigenvectors associated with distinct eigenvalues, remember those are linearly independent by our lemma in the previous video, but more to the point, these eigenvectors coming from distinct eigenspaces are orthogonal with respect to the standard dot product. Right? And if you're using complex vector spaces, you're going to have to use the conjugate dot product. Okay. And third, and perhaps most importantly, Rn can be represented by a basis of eigenvectors of A with respect to the dot product. It's an orthonormal basis, even. So not only do we get an orthonormal basis from Gram-Schmidt if we want it, if we have a symmetric matrix, then those orthonormal coordinates are, you can actually choose orthonormal coordinates that are eigenvector coordinates. So in particular, all symmetric real matrices are complete and they are real diagonalizable. And this is huge. The fact that we get real eigenvalues is extraordinarily important for what is to come when we define the singular value decomposition. We need this fact. So let me outline for you here real quick that for larger systems, that this is going to be the case, that we do get real eigenvalues for a symmetric matrix. I can verify all of this. In fact, I'm going to. So let's go to MATLAB, and while MATLAB throws a hissy fit about connecting to the cloud, I will bring this back up over here and then come over here once the cloud loads. Voila. A is going to be 5 by minus 4 by 2, and minus 4 by 5 by 2, and 2 by minus 1. So here's A. I can go ahead and show you what the eigenvalues look like. So eig A. And sure enough, if I wanted to create a D matrix, I could. D is equal to diag of eig of A. And there it is. It creates a diagonal matrix of the appropriate size, whose diagonal elements are whatever's inside the argument here, whatever the list is. So sure, we can then go ahead and construct the kernel here. So the null of, what would it be, A minus 3 times the 3 by 3 identity matrix. So A minus lambda I, awesome. We'll call this guy V1. Same idea, null of A minus 3 star the 3 by 3 identity matrix. There's another vector score. This is going to be V2. And then we'll do null of, okay, so the last eigenvalue is lambda equals 9. So this is A minus 9 times the 3 by 3 identity matrix. Booyah. So there's V3. Excellent. So I can go ahead and say that this matrix S is equal to V1, V2, V3. So I can go ahead and construct that guy no problem. Or I could go ahead and compute, oh shoot, what do I want to call this? I'll do an E for right now. UEV. This is going to be SVD of A. This is going to be a little bit different, tiny bit different, but you'll notice some similarities between these vectors. I effectively just computed a diagonalization for A transpose times A. So this matrix. Why? I'll show you in a little bit. But either way, this is a way that you can go ahead and compute, let's see. Yeah, this is a way that you can go ahead and compute eigenvectors and eigenvalues in MATLAB. And eigenvec? Nope. I can't remember the name of the function off the top of my head. I'm pretty sure MATLAB has a full eigenvector suite here. Produces D, produces full, okay. Yeah, so actually this is exactly the same function. So S by D here is going to be eig of A, and it goes ahead and it actually computes that entire suite. So it does this all without us having to compute null spaces. So feel free to use this overloaded expression to create your eigenvector bases if you would like, and we can verify. V9 here is going to be the third column of S, right? So V3, oh, sorry, S of all there and there. So this is going to be a multiple of 1 by minus 1 by 0 that we have over here in the notebook. So indeed, that gives you the eigenvector that we would like to use. And we come back down, you can see a very similar phenomenon occurring for the eigenvector associated with 3 and for minus 3. Great. So MATLAB is still useful. Wonderful. And we can note, oh, I shouldn't have done that. We can note that all three of these guys are orthogonal, right? And how can we do that? Well, go check it in MATLAB. S here is the matrix of eigenvectors. So if I do S prime times S, lo and behold, I get the identity matrix. So this is an orthogonal matrix, S. Awesome. So we do wind up with the correct thing. But we do get orthogonal eigenvectors, and in fact, MATLAB computes an orthonormal collection. So let's see. A symmetric matrix is positive definite if and only if its eigenvalues are strictly positive. So now we have an alternative characterization of, we have an alternative characterization of positive definiteness. We can go through this very quickly. That if K is positive definite, then notice what happens if we send any vector V through this bilinear form, V transpose K times V. Well, K times V, if V is an eigenvector, then I wind up with lambda times V for KV. And the lambda factors outside of the transpose here, so this is lambda times V transpose V, and this is exactly equal to lambda times V dot V, which is exactly lambda times the norm of V squared, which is exactly what I have on that line in the proof. So indeed, this lambda must be positive. Okay, cool. Going backwards, if all these guys are positive eigenvalues, then I'd like to show you that K is positive definite. So if we were to go through this in coordinates, right, we choose an orthonormal basis. Yep, so we choose an orthonormal basis beta for these guys with respect to the standard dot product, which is guaranteed to exist. Let's see, am I doing this by lambdas? Yeah, so I'm creating a, so specifically this is a symmetric matrix so that I guarantee that I have an orthonormal basis of Rn. That's why this guy exists. And doing this with respect to the standard dot product. So if I have an arbitrary vector V of Rn, I need to show V transpose Kv is a positive number. So if I do this out in these orthonormal coordinates, I follow the computation down and down and down, and I will see that I wind up with the following expression here, which is a way, oh shoot, have I written it down correctly? I'm looking at it, yeah. So this expression here, this ui transpose times lambda j times uj, this is lambda j times ui transpose dotted with uj, or sorry, ui dotted with uj, and this is exactly equal to the delta ij. So lambda is in delta, so delta ij is only ever going to be non-zero. It's going to be 1 when I is equal to j, so this is exactly equal to lambda j. So otherwise, I can go ahead and ignore every other term in this double sum, which is exactly why I come down to a single sum here at the bottom. Okay, so indeed, this guy is the sum of a whole bunch of positive eigenvalues multiplied by square numbers. And remember, this is a real vector space, so all the CIs are real numbers. So this is indeed going to be positive. Okay, if all the CIs were 0, then we were dealing with a 0 vector in the first place, and that's fine. I mean, V transpose KV would just be 0, which is still within, it's still within the restrictions of or within the definition of a positive definite matrix. But let's see. This is in accordance with a trace and determinant positive criteria, and we may or may not have seen this because I assigned it as an extra credit problem. But there is a way to say that for 2x2 matrices, that if your trace and your determinant is positive, then you have a positive definite matrix. And you're welcome to use that criterion if you'd like, moving forward. But as a corollary to this theorem, that we get positive definite matrices, symmetric and positive definite is equivalent to saying that your matrix has strictly positive eigenvalues, then sure, if we have a symmetric matrix, symmetric matrix A, and you choose the orthogonal basis that is guaranteed to exist by this theorem upstairs, right, by this theorem, then what we can do here is associate with the non-zero eigenvalues the first R vectors. So U1 through UR are going to be all non-zero eigenvectors associated with non-zero eigenvalues. And then the remaining guys, UR plus 1 to UN, is going to be is going to be a basis for the kernel, right? This is going to be for E sub 0. Then R, the number of eigenvectors that we wind up with corresponding to non-zero eigenvalues, is going to be the rank of A. And beta 1, consisting of those vectors, is a basis for the co-image. And in particular, beta 2 is going to be a basis for the kernel, which is equal to not the co-image, but co-image perp. So I should actually fix that in black. It's the orthogonal complement of the co-image. There we go. Cool. So on the next page, I address why we care. So yeah, sure, symmetric matrices are really, really great just for that previous theorem. But it's the spectral theorem that we care about most. And this is a big deal. Put lots of stars next to this in your notes. This is a huge theorem, so much that it has a name, and it's not named after a person. That should be enough for you. This is a huge deal. It's a common enough theorem where many people had a hand in showing it, or that people used it before it was actually named. So we can't really attribute it to any one person necessarily. Hence, it has a spectral, or it has a non-name theorem name, which is kind of weird saying that out loud. But if we have a symmetric real matrix, then there exists an orthogonal matrix Q and a diagonal matrix D such that A can be diagonalized with this orthogonal matrix Q. And this really is just a restatement of this third fact here, that Rn has an orthonormal basis, right? So before we were using Gram-Schmidt to come up with that basis, but now we can use diagonalization to come up with an even better orthonormal basis. And specifically, that's exactly what we're doing with the matrix Q. The Q matrix is an orthonormal basis. Okay, so this is another gigantically huge important factorization for us. So just like we had LU encoding Gaussian elimination, Gram-Schmidt, or the QR factorization encoding Gram-Schmidt, now we have the spectral theorem talking about eigenvector decompositions. So this guy, we're close. This isn't quite the factorization that we want to get to, because we want to do this for rectangular matrices, not just square matrices. But this is an important factorization. and it's really easy for us to solve to solve our linear equations with these systems, right? It's just a combination of it's a combination of a matrix multiplication, two matrix multiplications, and a linear solution, dx equals y. So this is going to allow us to still solve systems in order n squared time if we so choose. So this might remind you of the LDV or the LD and L transpose decomposition that we had before, but remember, these are encoding different things. LD L transpose is encoding Gaussian elimination. QD transpose will be encoding eigenvector and eigenvalue, so spectral information about A. So they are entirely different factorizations, so bear that in mind. And just to remind you, before that we had an example that did exactly this. This is an eigenvector decomposition, but it's not an orthonormal. If I choose this to be Q, then Q transpose times Q is actually going to be, I believe, 2 by 0 by 2. So I don't get the identity matrix, so this is not an orthonormal set of eigenvectors, even though it is just orthogonal. But I can always go ahead and scale down my eigenvectors by their lengths in order to create the orthonormal columns here. And this, to remind you of that square, why that commutative square is important, it's telling us a little bit about geometry. So remember how we characterized orthogonal matrices back in chapter 4. We have a similar characterization for what diagonal matrices do. Diagonal matrices are just going, like when we multiply by a diagonal matrix, we are scaling a vector along coordinate axes. So we get a scaling in D. Q and Q transpose are both orthogonal matrices. And orthogonal matrices, remember, are reflections and rotations. So A is effectively being broken down into a combination of rotations and scalings. So A is, when we say A is broken down as, or factored as QD transpose, it says rotate, scale, and then rotate back. Right? Remember, we're reading these from right to left because that is the order in which this matrix hits a vector through multiplication. So to show you what that commutative diagram looks like physically, if I'm looking at my two eigenvectors here, so this one will be column 1, this will be column 2 of the Q transpose matrix, then if I'm multiplying by A, then this is going to be what happens when I kind of rotate so that these guys are along coordinate axes. I scale along those coordinate axes, and then I rotate back. Okay? So technically, I suppose that's Q transpose DQ. Very, very technically. But again, it's a matter of perspective, which vector you take to be the coordinates and which ones you take to be the inverse transformation. But if I think about this in terms of a circle, or if I think about how this transformation affects an entire collection of vectors sitting inside of a disk, then I'm rotating a disk, scaling out the disk by different amounts in different coordinate directions, and then rotating this new object, which is an ellipse. So this Q transpose decomposition is telling us a lot about the geometry of what this transformation does. And we are going to use that geometry to our advantage. These principal directions, or principal components as they're called, carry a lot of information about data sets. And we'll see exactly how when we start talking about your low rank approximation theorem that I talked about a few videos ago. So we're going to go ahead and end the video here for right now, because in the next video we are going to go ahead and start talking about the singular value decomposition and how it's used. So